Okay, welcome to the second half of this lecture. This is going to be lecture 9b, flow regimes and flow rate, and we're basically going to focus on this computing volumetric and mass flow rate. So the volumetric flow rate is probably the most important thing you'll be able to do from this class. This needs to become a standard just thing. Like it's going to show up on pretty much every problem. So if there's things that you need to learn from this class, I would say that this is it. Okay, so do not slough off this bit right here. Okay, so we're going to define it real quick. And the volumetric flow rate, which we almost always give the symbol Q. Okay, and you may not like that. I think that's totally reasonable. I don't know why. I don't know who chose Q, but it's always a capital Q. Okay, so don't get confused when I start using Q all the time. Okay, Q equals the volume passing a point divided by time. Okay, so the standard easiest way to do this, well, I could imagine a river. In fact, I do imagine rivers all the time. It's kind of what I think about. So here's a river, and if you wanted to, you could decide that this is your point. This is point 1 or something. And what you would do is you'd say, okay, well, I'm going to measure for an hour. Okay, so Q equals 1 hour. And you're going to somehow calculate how much crosses that line over that hour. And let's suppose it's, 1,000,000 cubic feet. Okay, and then you could say, well, Q equals, 1,000,000 cubic feet per hour. We don't usually use cubic feet per hour. So you'd probably have to change it to like 400 and, I don't know, something like that. Cubic feet per day, maybe. So you could do cubic feet. I don't really know how let's do feet cubed per day if you wanted to. That's not really all that great. But you could also make it what we typically do, which is CFS. Okay, so in this case, if you were to do cubic feet per second, which is much more typical, Q equals 24 million, cubic feet per second. Okay, for a river, that would be much more typical. That's obviously a tremendous, maybe it's not obvious to you, but that's a tremendous flow rate. I'm not sure there's a river in the world that does that. Maybe the Amazon does, I don't know. Typically in this class, we work in pipes because we work in a lot of engineered systems. So you're kind of thinking about, usually it's kind of like a cross-section. Okay, so maybe we're looking at this cross-section right here. And if we say the pipe has 3 CFS, that means in 1 second, 3 cubic feet of water passed this, cross-section right here. Okay, so that's the conceptual idea for what it is. It is always measured in basically volume per time. So Q is measured in, usually you could do L cubed over time. Okay, so that's volume per time. Sometimes in the English system, you will see gallons per time, gallons per second, or something along those lines. If you get gallons, convert them to cubic feet, okay, because that's going to be way easier. All right, so next up is, how do we define Q mathematically? Q is a scalar, first of all, so that's an important thing. So this is a scalar. It does not have a sign. It equals the integral over an area of V dA. Okay, so that's one way to define it. And so if you're kind of like, well, if you're not really that comfortable with your calculus, what that means is if we've got a little area right here, okay, we can multiply that little area times the velocity going through it, like that. Okay, and that'll give us the flow rate through that tiny little area, but then we're going to integrate it over the entire area. So basically we're going to add all those up. Okay, so this is one way to define it. Another way to define it is with a dot product. Dot product is probably a better way to do this. Q equals, it's an integral again, but it's V dot dA. Okay, we're going to integrate this. Well, it's being integrated over the area. Okay, and it's the same drawing as what I did right up here. But let's imagine this is our cross section. I'm just going to kind of zoom in on it. Okay, and the reason there's a dot product here, and some of you are immediately thinking like, okay, dot products, I know I take the magnitude of the velocity times the magnitude of the area, and then I see either a sine or a cosine. Well, what it means is we're trying to figure out how much fluid is flowing through this cross section. Okay, so if you imagine our little dA here. Okay, dA technically has a direction, and the direction is like this. Okay, sometimes it will be forward, sometimes it will be backwards, and we'll talk about that later. But if your velocity is on an angle to that dA, so if it's on an angle like that, okay, theta, say, well, only so much of the velocity may be going very, very quickly, but not all of it is being used to go through that area, right? Some of it is going to the side, and that part doesn't matter. Okay, so the only part that matters is the part that's going forward. So that indicates that we need a cosine here because we need the adjacent side of the triangle. Okay, so if you did this as a if you wanted to break it down into a dot product, basically it would be the magnitude of V times the magnitude of A times the cosine of the angle. Okay, so if you wanted to do a dot product. Now, what comes out of Q very often is that we're going to use, a lot of times, the easiest way, not always the appropriate, okay? So we're going to have to focus on that. But the easiest is to do Q equals V average, okay, so that's the average over the cross-section, times the area, okay? And V average is defined as Q over A. Now, this is always, okay? This is not always appropriate. And the reason, I guess it's always appropriate if you know the V average, but you don't always know the V average. So for example, if I gave you a problem that looked like this, here's a pipe or a river or whatever, and I told you the flow is like this. Okay, well, you might want to use this because the equation looks nice and pretty. Okay, because maybe you can pretty easily calculate the area of this pipe. Maybe it's a circle. Okay, and you're like, okay, well, I just want Q, so I'm just multiply times the velocity. But what's the average velocity here? It's unclear. Okay, so in this case, you can't do this method. You have to go up and do one of these two, okay, whichever one works for you. Okay, so that's maybe not problematic, but that's just the way it is. As we get further into the semester, I'm always going to give you this, okay? And so this will be the way that you typically do it. But for now, we're going to have to deal with some integrals. All right, so that's the Q, okay? So hopefully you kind of got a conceptual idea of what the Q is. Now we're going to talk about the mass flow rate, which doesn't have its own symbol, okay? So so the mass flow, I guess it kind of does. It's really derived from another one. So you might have seen this in some, books, m dot, so that means the change in mass per time, okay? And so basically what we're going to do is we're going to take the regular flow rate. Okay, so that's Q. So that's volume per time. And I'm going to say, well, if I multiply that by the density, so I've got volume per time, and I'm going to multiply that by mass per volume. So now I'm going to get the amount of mass that's crossing that same cross-section. So we could write this as rho. How do we want to do Q? Well, we'll do Q as average velocity times the area. Okay. And more specifically and more typically, if you have to integrate, or more generally, I guess, if you have to integrate, it's rho v dot dA, okay? And you're integrating over that area, okay? Note that this has units of mass per time, okay? So it should be kilograms per time, or it should be slugs per time. Do not, avoid the slugs, okay? One thing that I want to note between these two mass flow rate and volumetric flow rates is that mass is conserved. Okay, this is key. Okay, volume is not. But there is a time when volume is. Okay, unless the fluid is incompressible. Okay, and we'll get to a lot of a lot of times that will demonstrate that. Okay, so basically, what's going to happen is if the fluid is incompressible, then let's suppose I take a pipe and I'm like, okay, well I got a pipe, you know, and I got some mass flowing in here, so I got a mass flow rate rho Q on this side, and I've got a rho Q on this side. Okay, so if mass is conserved and this pipe is full, then that says that what goes in must equal, let's call this 1 and 1, 1 and 1, must equal what comes out, rho 2 Q2. Okay, but if this is, let's put some 2's over here. But if this is, but if this is incompressible, then what happens is these rows are the same thing, so algebraically I can cancel them. Okay, and now I've got a conservation of volume. The volumetric flow rate in equals the volumetric flow rate out. Okay, try to say that twice. It's really not that hard. Okay, so let's do some example problems, and then we'll call it a day. Okay, so oil flows through a 30-inch pipe at 8,000 gallons per minute. Okay, the first thing you want to notice when you see things like this, if you see gallons per minute, you don't want to work in units like that, so we're going to want to convert that. Your job here is to find Q, so that's the volumetric flow rate in cubic feet per second. You want to find V bar, so that's the average velocity through that pipe. And then you want to find M dot, so it's the that's the mass flow rate. Okay, so I like to draw pictures when I can, so even though there's really not much to say about this picture. So this is oil flowing through the pipe, 30-inch pipe, okay, so 30-inch diameter, okay, at 8,000 gallons per minute. I'm going to go ahead and, before we even begin, I'm going to convert this. So that's 2.5 feet, okay, so we're going to use that instead because I don't want to deal with inches. And gallons per minute, I'm going to convert, so that's 8,000 gallons per minute, okay, and so minutes are to get to seconds, so we're going to go 1 minute, 60 seconds, and let's see, gallons, 7.48 gallons per cubic foot. Okay, so that kind of converts that for us nicely. So that is 17.8 cubic feet, so we've got the cubic feet per second. Okay, so we just converted that into units that make sense for us. And then we go back over here, and now let's think about what it is we're looking for. Oh, well, all right, we actually accidentally just solved it. Okay, so for A, we want the flow rate in CFS. Now, I should have noted that this right here was already a flow rate because we had volume per time. Okay, but I converted it. So now we're at flow rate of Q equals 17.8 CFS. Beautiful. Okay, that's part A. Okay, part B, we want the V bar. Okay, noting that Q equals Q over A. Okay, a second ago I had this written as Q equals V bar A. Okay, so I just rearranged that equation. And Q is 17.8 CFS. Okay, I'm divide by the area. So the area of a 2.5 foot pipe is, so you can use pi r squared, or you can do pi d squared over 4. We're more often than not going to do pi d squared over 4, like that, because we're usually given the diameters of pipes, and so rather than dividing them by 2 all the time, we're just going to divide the square of it by 4. Okay, so if we plug that into a calculator, okay, so what we're looking for here is the average velocity. Okay, it doesn't tell us anything about what the velocity is at a particular point. It just says that on average, we end up with 3.63 feet per second, or sometimes you'll see that written as 3.63 feet per second, like that. Okay, either way. Okay, and then last, we want M dot. Okay, so the mass flow rate. The mass flow rate, luckily, is usually pretty easy once you have okay, so the mass flow rate, which equals rho times Q. Okay, so usually once you have Q, the mass flow rate is pretty straightforward. We have one more piece of information that we haven't used, which is the specific gravity of the oil. So M dot equals S oil. So this would be the rho of the oil. So this would be S oil rho W times Q. Okay, so once we are ready with that, we can say, well, m dot equals, well, the S of the oil was 0.86. 0.86. The row of the oil, okay? Think for a second, what is the row of oil? I mean, of water. What's the row of water? What's the row of water? We're in the English system, okay? So it's going to be 1.94 slugs per cubic foot. Some of you guys are resistant to this word slugs, okay? And I know that. You're just going to have to, figure it out, okay? Now Q is the flow rate. So what was that earlier? 17.8 CFS. Okay, noticing the cubic feet on top and bottom will change, and we'll get slugs per second. So m dot equals 29.7 slugs per second. 29.7 slugs per second. Now some of you are saying, can't I do pounds mass? Pounds mass is not a real unit. We don't use that in this class, okay? I don't care what you use in other classes. It's ridiculous, okay? It's a ridiculous unit. All right, so I did that kind of quickly. But there's not really a whole lot of discussion to be had here. They're just, it's kind of like numbers. Like at this point, there's not even a lot of intuition where you can look at it and go, well, should this number be large? Or, the numbers are pretty large. 29.7 slugs per second, that's an awful lot. But you can also see, the water's really cooking through there. Every second, 3.63 feet per second. Okay, so that's more than a meter per second. That's a lot of water. Okay, let's do another example. Okay, so air. It's got a density of 1.4 kilograms per cubic meter. Travels in a 1 meter square duct with a vertically linear velocity profile maxing out at 10 meters per second in the center of the duct. I probably wouldn't give you this problem only because I think the wording is a little bit confusing on a test or a quiz, but I could give you something, like this. Find Q and CFS, V bar, so it's the average velocity, and M dot, which is the mass flow rate. So what this looks like, again, we're going to draw a picture before we begin, and this is why I wouldn't give it to you, because I think it's hard to kind of figure out what that picture is. So this is what the duct looks like, 1 meter by 1 meter. And air is going into or out of the board, into that duct. Okay, now if I draw it from the side, okay, so we're going to keep it at 1 meter, then what's happening here is I'm going to plot the velocity profile. And basically, it's linear, so it's a, what's it say? A vertically linear velocity profile, maxing out at 10 meters per second. So vertically linear, maxing out at 10 meters per second. Okay, now it's unclear to me without, if I'd given you this problem and you had not been able to, basically take these words and make this drawing, I would understand. Okay, but a vertically linear velocity profile you should be able to understand, but it would need to say it was vertically linear from the bottom half. But anyway, so what's interesting about this, there's a few interesting things. First of all, the reason that the air has zero velocity at these points is because of the no-slip condition and the viscosity of the air. However, we note that in this case, it doesn't seem to have a no-slip on the sidewalls, okay? Because it's, it's only varying linearly. So this is basically impossible. This was just done this way to create a good problem. Okay, so something that you could solve. Okay, so the first thing we want to do is we want to get Q. Okay, so let's just start solving the problem. So A, we want Q. Q equals what? Okay, so the temptation at this point is to say, well, Q equals VA, because that's the easiest. However, we can't look at this. Okay, remember that V bar means V average. And I can't look at this and just automatically know what V average is. Okay, so it's probably something like this. And in this case, you could guess 5 meters per second and you would be correct. But if this were a circular problem, you would not be correct. 5 meters per second. So, but let's assume that it was not something what if the velocity profile weren't linear, okay, or something along those lines. So what we're going to need to do here instead is we're going to need to actually integrate. Okay, so this is no good. So we'll do Q equals V dA. Well, let's Let's do it without the symbols because we're just going to multiply. And the reason that we're not going to do the dot product here is because the two things are in the exact same direction. Okay, so the area is pointing in this direction. Okay, in the exact same direction as the velocity. So we don't need to worry about a dot product. So one of the problems here is, okay, the area is pretty straightforward because, well, we know a lot about this thing, 1 meter and 1 meter. It's actually a little bit less straightforward than that, but the velocity is an issue. So I'm going to go over here and we're going to kind of define the velocity. So the velocity here, okay, well, I'm going to use some high school era math that maybe you have forgotten, okay, and that's going to be v equals my plus b. So I'm going to assume that this thing is a linear velocity profile, which means in high school you did y equals mx plus b. So in this case, we're not in the x-coordinate, we're in the y-coordinate, okay? And let's see, so at the bottom, the velocity is 0 when y is 0 plus b. So that means that b equals 0, okay? So I'm using this point right here and plugging in the velocity of 0, which we can see from the graph, and at y equals 0. And so I get b is 0. Okay, so now I know v equals my. Okay, so now I want to find out m. I want to get that slope. Okay, so when y is a half, 0.5 meters, okay, the velocity is 10 meters per second, like that. Okay, which means that m is going to equal 20, and then per second, so those are units on m. So I can say that the velocity then is, so I'm going to go back to this equation right here. I'm going to plug that in, and I got v equals 20 per second times y. Okay, and that's for 0 to 0.5 meters. Okay, that's in y. Okay? So that's a little bit interesting, I would say. I hope so. Hope you... So it's got ugly units. It's an ugly equation, but that's the one we're going to have to use. Okay, so we're going to basically take that one and plug it in right there. All right, so I'm not going to deal with that for a second. We're going to come back to that. But what I want to do now is I want to deal with this dA. Okay, so the way that you deal with the dA, I'm going to leave the v as just v for now because I don't feel like writing it out. And the dA is going to become dx and dy. Okay, and so, you know, if this is the x direction, I guess, yeah, we'll call that the x direction. Why not? Doesn't matter. Okay, this is flowing, I guess, in the z direction. And so we have to deal with these two things one at a time. And so the dx is going to go from 0 to 1 meter. And the dy, well, we're going to deal with that in a second. So what I'm going to do for the dy is this. I'm going to rewrite this as 0 to 1 meter v dx dy. And what I'm going to do is, because this is symmetric, and I'm looking for a, oh, I can't spell symmetric. Okay, you know what I meant. The dy, we're going to go from 0 to 0.5. I'm not going to go all the way up because I'm going to multiply this whole thing by 2. Okay, because my equation is only valid for the bottom half. Okay, and so that ultimately is how you solve it. Now, what's interesting here is that v does not vary in x, so I don't really have to do much with this in the x direction. So I could just note that it doesn't vary. So when I integrate this first thing, what's going to end up happening is I'm going to have the integral from 0 to 0.5 meters of, let's see here, v. Yeah. And what's going to happen is this whole integral, because v doesn't vary in x, it's basically I'm just going to multiply it by the change in x. Okay, so I'll call that change in x, okay, or the width, or whatever you want to call it. Or capital X might be what I would call it. So dy. Okay, and we'll have a 2 out here, and q equals this. Okay, so basically what I've done here is I've noticed that since this doesn't vary in x, this and this combine basically to just give me 1 meter. Okay, and 1 meter is that delta x right here. And it can actually be pulled out all the way out to the very front. Okay, and we can end up with 2 meters out front. Okay, because that delta x is just a 1 meter. So I get 2 meters times integral 0.5 over 0 dy q And then I just need to plug in that V. So I'm going to plug that V in right here. Okay, 20 over seconds times Y. Okay, so this is so it's just a constant times, you know, a number in this, or a constant times a variable, in this case the Y. So this becomes, let's see, so we're going to go Y squared over 2, right, over 2. Okay, times 20 over seconds from 0.5 meters to 0 meters. And then we're going to multiply by 2 meters out front. Okay? So when we plug in the 0.5, we end up getting a quarter. Quarter times 20 is 5. 5 times 2 is 10, divided by 2 is 5. So Q equals, and if we keep track of all the units, we end up with 5 cubic meters per second. Okay? Ugly, right? I highly recommend that you go through all this on your own and make sure that all those steps made sense to you, especially this one right here, where basically I decide that, hey, look, V doesn't vary in X, so we just pull it out, okay? Okay, so that's the first part. The second part is we want the average velocity, V bar. If we'd had that from the beginning, this would have been a much easier problem, but we did not. Okay, I noted I already knew the answer, but that's beside the point. So Q equals average velocity times the area. Okay, so that's 5 cubic meters per second equals the V bar, what we're looking for. And the area, well, this is a 1 meter by 1 meter square. So V, if you do the algebra here, is 5 meters per second. Okay, noting the units all work out. Okay, the last thing we need is let's see if we go all the way back up here. We need the m dot. Okay, m dot. So m dot is going to be, so that's the mass flow rate, rho times Q. Okay, so the rho is, I think it was given as 1.4 kilograms per cubic meter. Okay, times the Q, which is 5 cubic meters per second. Okay, so if we multiply that, it is an exact 7 kilograms per second. Okay, and I'm sure that you all are happier with kilograms than you are with slugs, but it's no different. Okay, just use the slugs. If you use pounds mass, it's going to be different, and there's going to be all kinds of weirdness that you have to deal with. Okay, so that's my recommendation. All right, so this is the B portion of Lecture 9, Lecture 9b. So it's a lot of mess, but it's really important. So anyway, I hope you all are having a good day, and I'll talk to you later. It's office hours right now. There's nobody here. So please come to office hours. I'll talk to you later. Bye.